All right, we're live. Do y'all feel it? Do you sense it? You excited? You nervous? We learned these on Friday. Let's see if you remember them over the weekend. Without looking, the derivative of sine is cosine. Perfect. Perfect. The derivative of sine is cosine. And then, of course, the derivative of cosine is? What kind? Oh, negative sine. Yeah, negative sine. We even derived it on Friday. The thing that I told you also on Friday, which maybe you didn't hear, but that if anything starts with co or inverse co or arc co, then it's going to have what type of derivative all year long? A negative, right? And if it doesn't start with co or inverse co or co, it's going to be a positive derivative. That'll be helpful as we move forward. Right now we're just learning sine and cosine's derivative. Now that we know the rule, we can combine it with the other rules that we've already learned, like the power rule, yeah? To take derivatives of bigger and better functions. Like, example 10a. We have y equals 2 sine of x plus 7. Now, quick word here again. If I had written it as 2 sine of x plus 7 like that, would that be the same as the line above? Yes. By default, if there's no parentheses, you just take the first term after the trig function to be the angle. And if you intended the angle to be x plus 7, then you'd have to have parentheses around the whole thing. So with or without the parentheses, it's the same. I have two terms. Do either of them need to be rewritten? Well, the 2 sine of x, right. We know that there's a constant rule. So the derivative of 2 sine of x is going to be 2 times the derivative of sine of x. That's what the constant rule said. So we've got that. So what becomes of the all-important left side? Y prime, the left side, is y prime or dy dx. And now the right side, the derivative of 2 sine is 2 cosine of x plus what? 0, which we don't even have to write. There you go. See how easy it is if you have your sine rule memorized? Piece cake. Questions on A? All right, letter B. F of x equals x plus cosine of x. I have two terms. Do either of them need to be rewritten? Nope. So the left side becomes f prime, and the right side, the derivative of x is 1. Okay, the power rule works, but you can also think of it, remember, as just a line with a slope of 1 everywhere, 1x. The derivative of cosine, negative sine. And there it is, f prime of x is 1 minus sine of x. Easy. So far, so good. Quiz Wednesday? No. Tomorrow? I won't quiz Wednesday. Thursday. I like Thursday quiz because that's when the worksheet's going to be due. That's right. You get all day to recover, and then Thursday you come in and take a quiz. All right. Letter C. We got g of x equals 2 sine of x halves times cosine of x halves. Uh-oh. Kind of have a problem here, right? What are we doing with these two functions? Yeah, we're multiplying them. It is. There is no product rule that we've learned yet. I can't just take the derivative of that times the derivative of that and multiply them together. Besides, the angles are not just x, they're x halves. And I haven't taught you the sine of x halves rule. So what we're going to have to do is find some way to rewrite this into something that's either sine of x or cosine of x, because those are the only two rules that we have. So do you recognize it as anything? Yes, hopefully you do. We had an identity in pre-cal that said 2 times sine of x times cosine of x was equal to sine of 2x. That's your double angle identity for sine. And you still have to know that one. Cosine of 2x, for what it's worth, was the one that looked a lot like Papa Pid, but it was minus sine squared. Cosine squared minus sine squared. Now this is the one we're going to use. X doesn't have to be x. X could be anything. It just says 2 times sine of blob times cosine of blob is equal to sine of twice the blob. Well, we have 2 sine of blob cosine of blob. Our blob happens to be x halves. By the double angle identity, that becomes sine of 2 times the blob, right? And it's equivalent. Now, if we simplify that, what is 2 times x halves? Sine of x. Ooh. The derivative now is easy because that function g of x is nothing more than sine of x in a really clever disguise. So now G prime would be cosine of x. And we're done. Nothing to it. All right, so those identities, these are about the end of the ones that y'all need to know for this class. The double angle identities. Okay, any questions on using the two new rules, the sine rule and the cosine rule? All right, let's put them to good use. Here's a nice little application. If f of x equals sine of x, find the following. A, the slope of the graph at 0. The slope of the graph at 0. That would be the instantaneous rate of change of the graph at 0, right? What do we need for the instantaneous rate of change, or the slope at a point? Well, if we're writing the equation, we need a slope and a point. I just want to know what the slope is. Derivative. So if f of x is sine of x, then f prime of x must be cosine of x, yeah. And now if I want the slope of sine at 0, that's just f prime of 0. And notice how I'm writing that. On the left side, it's just as important. That's cosine of 0. And if you look at your watches now, of course, it is unit circle time. Yeah, and cosine of 0 is 1 from the unit circle. So let's see what that means graphically. Sine of x, which is Sahala, right? We all remember Sahala? It does have waves. It's the sine wave. Looks like that. What we did is we just found the slope of the tangent line right there at 0. And we know that its slope is 1. So the graph of sine of x launches out of the origin with an angle of what in degrees? If the slope is 1. What's that? 45 degrees. Right. A slope of 1 is 45 degrees. So that does end up being the optimal angle. If you want to throw something near the surface of the earth and you want it to achieve the maximum horizontal distance, you should launch it at a 45-degree angle. And neglecting topography and air resistance and birds coming by and catching your object in mid-flight, that would allow you to get the farthest horizontal distance. We'll prove that, yeah, baseball or football or a calculus textbook, whatever you're throwing, your little brother, you can get him to go farthest by throwing him at that angle. Okay, f prime is 7 pi 6. What does that mean graphically? F prime is 7 pi 6. It's the what of the who at 7 pi 6? Yeah? Well, let's see on the graph, though. What are we trying to find? Here's pi. Where does 7 pi 6 live in relation to pi? To the left or to the right? Just to the right. Yeah, so it's going to be right around here. It's going to be a negative slope. And we want to know exactly how fast is the graph changing there. Well, not a problem, because all I got to do is plug it into my handy-dandy derivative. So that's going to be cosine of 7 pi 6. And again, it's everyone's favorite time, boys and girls. It's not male time, but unit circle time. What is cosine of 7 pi 6? Negative square root of 3 over 2. Good. Is that a reasonable slope for over there? Oh, we drew it? Yeah, it's perfectly reasonable. In fact, it's correct. It's awesomely correct. Did y'all grow up in the Blues Clues era? Did you get excited when it was mail time? Well, that's why I said mail time, because I heard you say something about Blues Clues. That's why I brought it up. Yeah. Yeah. Do you know the song? Here's the mail. It makes you wanna shake your tail. Mail time. I don't know. Anyway, all I know is that Steve went off to college at some point, and his brother came in, or his cousin came in. Steve was at college. All right, that was magenta, and then there was Periwinkle the cat, right? Okay, maybe after the AP exam we can kind of brush up on Blue's Clues. Paprika, right? That's salt and pepper's little baby. Yeah. I've tried that at home, though. You mix salt and pepper in a bowl, you do not get paprika. It's not a good substitute when you're cooking, just FYI. All right, so on the half-open interval from 0 to 2 pi, we want to know where the graph has horizontal tangent lines. Well, notice that if we have our handy-dandy derivative, which we have written in our handy-dandy notebook, of course, instead of plugging in an x and finding the slope there, we can use it in reverse. If we know what we want the slope to be, we can set it equal and solve. So a horizontal tangent line has a slope of what? 0. And that is probably one of the most important slopes we'll be using all year long. So instead of plugging that in for x, I'm going to set it equal to 0. And now, again, it's unit circle time. Where is cosine equal to 0 on the unit circle? At what angles is cosine 0? Pi halves and 3 pi halves. Good. On the y-axis. Remember, cosine measures the horizontal width of the triangle, and when it's on the y-axis, you've collapsed it to nothing. And if you come up here to the graph, pi halves and 3 pi halves, but of course. Who said that? I think that was Pepper, right? You talk like that? We have horizontal tangent lines. But of course. No, it wasn't. Was that Pepper? I don't know. It's been a while. Hey, let's talk about Dora the Explorer. Not really. Any questions on example 11? All right. Let's look at perhaps one of the most important applications of the derivative. It was the whole reason Newton got involved in discovering calculus to begin with. They did disappear. The slope of the tangent line was Leibniz motivation. Newton was all concerned about motion, things that changed. Here you go, Clay. Things that changed over time.
You have hair in there.
That's not hair, that's a wig. It's fake hair. All right. The instantaneous rate of change of one's position is called one's what quantity? Wow, look at his position change. He is really moving fast. He must have a very high speed. There you go. Or if he's traveling in a direction, speed in a direction is known as velocity. Good. So speed is a scalar quantity. It means it could be in any direction, but velocity is a vector quantity. It's speed with the direction. And we're going to restrict our motion right now to either left and right or vertically up and down. If you talk about someone's velocity changing, wow, look at his velocity change. He is whating? Accelerating. Good. So the rate of change of position is velocity, and the rate of change of velocity is acceleration. Those kinematic equations that you might have had in physics, if we let h of t be the height of a falling object at or near the surface of planet Earth, this is a function that gives us your instantaneous, it's the instantaneous position. At any given time t, plug it in, know where it's at. If you take the derivative of that, you get the instantaneous velocity equation. And that's what Galileo was vainly searching for. Never could get there. If you take the derivative of the velocity, you get the instantaneous acceleration, and it ends up being the second derivative of position, the instantaneous acceleration. So notice all of these are instantaneous. They're all functions of a single variable, which means if you know one moment in time, one input value, drop it in and figure out the function value at that moment. But before calculus came along, there was no way to find the instantaneous velocity or instantaneous acceleration equation. We had to use average velocity and average acceleration. And that's what we did in 2.1 when we developed the idea of the tangent line. This equation right here summarizes the relationship of all three kinematic equations. Let's review those kinematic equations. Maybe you memorized it, maybe you didn't. The height of an object falling near the Earth's surface was -1/2 g t squared plus v sub o t plus h sub o. V sub o was the initial velocity, and h sub o is the initial height. Lil g is, guess what? It's the gravitational acceleration constant, which is about 9.8 meters per second, or now 10, right, if you're in AP physics. So you can do more calculations without a calculator. And it turns out to be about 32 feet per second squared. Okay, so objects that fall near the Earth's surface will accelerate at a constant rate of about 32 feet per second every second. That's an empirically observable quantity. If you now want to take the derivative of that with respect to t, you can get your velocity equation. Let's go ahead and do it. If g is a constant, 1/2 is a constant, -1/2, what would be the derivative of that first term? Power rule, right? 2 times -1/2 is -1, g times t to the first, plus if v sub o is a constant, what's the derivative of v sub o t? Well, if it were 5t, what's the derivative of 5t? 5. If it were 10t, it'd be 10t, so it's just v sub o. V sub O is a constant, right? Because it's 1 times V sub O t to the 0. And then H sub O is a constant, and its derivative is 0. So there's your instantaneous velocity equation. And then, of course, the second derivative of height or position is the first derivative of velocity, which we can call acceleration. And what's the derivative of the first term? Negative g plus what? 0. And there you go. That is how, this is not how we know the gravitational constant is g. These equations were actually derived in reverse. This was empirically measured on planet Earth. And once calculus came into the fold, we were able to find the derivative in reverse, which is called anti-differentiation, and come up with the velocity equation and do it again and come up with the position equation, which is pretty nice. We're going to do that in the second semester, integration anti-differentiation. So right now, if you just know the height or the position of an object, you could take its derivative to find the instantaneous velocity, take its derivative to find instantaneous acceleration. Let's look at an example that was ripped from the headlines, okay? A calculus textbook is stolen. Dun, dun, dun. Where from? Not from the book room, from a museum. That's about where you have to go nowadays to find one. It's stolen from a museum. And you think that the thieves took it home so they can brush up on their derivatives? Because you know what else they did? They stole a 400-foot tower as well. Now, where do you get those? Museums. It's a tower museum. I don't know. And they stole the tower and the book so they could drop. They don't drop the tower from the book. That wouldn't hurt the tower. They're dropping the book from the tower, right, to the unforgiving pavement below. The height of the book, h of t, in feet at any time t seconds during the book's brief but painful plummet to earth. Now that implies that the book is hurting as it falls, not when it hits the ground. Why is that? It's a book, and as it's falling, it's telling itself, why me? It hurts on the inside. To first have been displaced from your home, right? They don't have feelings, but they have lots of problems. All right, it's given by this equation. Now, notice that negative 16t squared is basically negative 1/2 little g when g is 32 feet per second squared. 400 is your constant, so that's the initial height. Notice that there's no v sub o term there. There's no t term. So that means the initial velocity must be what? 0. If the term is missing, it's 0. These are thoughtful criminals. They take the textbook and rather than start it downward by throwing it, they're just they just drop it. So the initial velocity is 0. That's good to know. Answer the following questions regarding the book. Ready? For how many actual seconds, as opposed to fake seconds, was the book falling? Because you can answer fake seconds easily, right? 25 seconds. That's fake. We want to know actual seconds. Actual seconds. Well, no. How are we going to figure out for how many seconds the book was actually in the air? The book. Solve for t. Okay, well, let's see. I've got h of t equals negative 16t squared plus 400. You want to solve that for t right there as a function of h of t? You're right. We got to solve for t because we need to walk away with a t value. But what do we know about the height of the book above ground when it's on the ground for the first time? 0. Thank you. So you have to make that insight. When the book hits the ground, its height is 0. So we got to set it equal to 0. And now I have a parabola, a quadratic. I'll separate the variables. Still not picking up a calculator. Dividing through by 16, I get 416ths, which may simplify, but I spy something cool. If I take the square root, I get the square root of 416ths. And remember, when you solve for t by taking the square root, you want to at least consider the plus or minus. You always want to at least consider it. But are we really considering negative time values in this problem? Is that relevant? No, because these guys probably also stole a stopwatch, I'm guessing. And they started the stopwatch at 0 when they let go of the book. So t should end up being the square root of 416. Now, if you take the square root of 400 over the square root of 16, I'll do the denominator for you because I know that one. The square root of 16 is 4. The square root of 400, is that a good one? 20. Good. Now, 24th is also known as 5. So it took 5 seconds to hit the ground. That was nice. It's almost like these thieves deliberately stole a 400-foot tower instead of like a 350-foot tower, thinking that the students who were trying to crack the case wouldn't have a calculator, and that would come out to be a nice integer. Those are very nice, thoughtful, considerate thieves. I bet they even return the book, tower, and stopwatch when they're done with their experiment. It was borrowing without permission, right? And they say it's easier to get forgiveness than permission. So, sorry. Make that face. All right. So the book was falling for 5 seconds. Now the follow-up question. Just because it's part A doesn't mean there's only one thing being asked. Always look for a follow-up question. How many seconds did that feel like to the book? Probably forever. Remember, it was hurting on the way down. Okay, y'all can think about that over the evening. Should I have you write an essay? Think about describing the feelings of the book as it fell? Huh? I asked it. Will the College Board ask you that? No. But you know what? It's always nice to practice empathy, right? Just to put yourself into the other book's shoes. What was the velocity of the book in feet per second the instant it hit the pavement? The answer is not 0. Someone always says, well, it hits the ground, it's not moving, it's 0. Oh, thanks. Plug in 5 for what? Into which function? Not h of t. That'll tell you the instantaneous height. I should get 0, h prime. This is instantaneous rate of change of position, also known as instantaneous velocity. So, I'm looking for the velocity at 5 seconds, but before I can find v of 5, I need to find v prime of t. And I can't just use the letter v until I say, I need to find v of t. I can't use v unless I define it. So if h of t, remember, is negative 16t squared plus 400, here's what you need to show. You need to show h prime of t. That is required. If you want, you can now define v of t to be its derivative. Now, what that allows you to do is just refer back to v. But if you never define v, don't use v, because they only gave you h. That's going to be negative 32t plus what? 0. Now I can say v of 5, or h prime of 5. And if you plug it in, negative 32 times 5 is negative 160 feet per second. So there's your numeric answer. Now, why is the velocity negative? It's going down. The book is going down, right? Because what the velocity is it gives you the instantaneous rate of change of the book's height. So you could say at t equals 5 seconds, when the book hits the ground, the book's height is decreasing. The book's height is decreasing by 160 feet per second. So the speed of the book would be the magnitude of that, positive 160. But instead of saying the book's height is decreasing, we can refine that a little bit and say that the book is falling at a speed of 160 feet per second. Ouch, right? That's hitting pretty hard. Follow up. At this velocity, what happened to the page in the book that discussed the squeeze theorem? It probably got squeezed by the pages on either side of it, right? Very good. Very good. I think it was a smooth fall. No, there couldn't have been a cusp, right? Unless it like hit something on the way down. Think. What was the average, a seagull, right? What was the average velocity of the book in feet per second during its fall? Now notice it said average velocity during its free fall. It fell from t equals what to what? 0 to 5. Is this going to be an instantaneous velocity or an average velocity? Yeah, it says average during an interval. Does this require calculus? No. Average velocity is going to be the average rate of change of position. get in the habit of labeling your quantities. Your average velocity is your change in height, so it's your final height minus your initial height over the change in the time. This is your final height minus your initial height over the change in time. During its how long did it take to hit the ground? 5 seconds? This should be it, right? Now, this right here is going to be super important as we go throughout the rest of the year. This is called your difference quotient. This is kind of what we did in 2.1 when we were finding the average rate of change between those 2 points. You must show a quotient of two things being subtracted in order to get credit for your setup. In physics, we call the numerator the displacement. It's your net change in position, final position minus initial. And, of course, that's just your elapsed time. But it really is just the slope of the secant line on the graph of h between 0 and 5. Now, we can plug that in. h of 5, what was its height at t equals 5 seconds? 0. Minus what was its height at 0? 400-foot tower, right? All over 5. And if you simplify that, you get negative 80 feet per second. So that means that on average, the book was falling at 80 feet per second. Did it have to be going 80 feet per second the whole time? No. But if they stole another book that had cruise control, and they dropped one book starting at 0 and it ended up at 160 at the end, and the other book, as soon as they dropped it, if it was going 80 down the whole time, those two books would hit the ground at the same time. Of course, the second option is not really feasible. But here's my question to you. I know that the book actually started at 0 feet per second and ended up at 160 feet per second, right, in terms of the speed. But the average was 80. I know it wasn't going 80 feet per second the whole time, but did there have to be at least one time during its fall where it was going 80 feet per second downward? What theorem would guarantee that? It's got 3 letters. The IVT. The intermediate value theorem, right? Because the velocities are continuous, right? There's no way for the velocities to go from one velocity to the next without going through the continuum of all the velocities in between. And since it starts at 0 and ends at negative 160, by the IVT, there had to be at least one time where it was going negative 80 feet per second, right? And we could actually figure out the time by setting negative 80 feet per second equal to the derivative, right? Negative 32t, and solving for t. Now, whenever you do the IVT for slopes, for derivatives, for rates of change, you can use the IVT for the slopes, but it's also called the MVT. The MVT is like the IVT, but for slopes. And M stands for, not slopes, although we do use M for slope, from the French verb to climb, monter. It means the mean. Yeah, it's the mean value theorem. So it's the average value theorem, or the average rate of change theorem, if you want to think about that. That's coming up in the future. Okay, in the future, yeah. What was the acceleration of the book during its fall? Is that average acceleration or instantaneous acceleration? During its fall. Isn't that during the whole interval from 0 to 5? That should be the average now. Now, average acceleration doesn't require calculus. Average acceleration is just going to be the change in the velocities over the change in time. So your final velocity minus your initial velocity all over the change in times. And if you look at what the units are going to be, the units of the numerator are feet per second. The units of the denominator are seconds. And you end up with feet per second squared. So if it says average rate of change, hi, thank you. If it says average rate of change, like average acceleration, average velocity, it requires algebra, not calculus. And it's going to require the difference quotient. Now, what was the velocity when it hit the ground at 5 seconds? Negative 160, and V sub O was 0 all over 5. And if you calculate that, you get negative 32 feet per second, which is feet per second squared. It does make sense, right? Because what is negative 32 feet per second?
Gravitational acceleration.
Constant, right? It's the negative gravitational acceleration due to gravity constant. And it is a constant, of course, neglecting air resistance. Now, what this means, is also in terms of the velocity. If the acceleration is negative, that means that the velocity is decreasing. Right? This is the rate of change of velocity. So this means on average the velocity is decreasing by 32 feet per second each and every second. So for every 1 second that passes, the velocity is losing another 32 feet per second. Now how can it be that the velocity is decreasing but the speed is increasing? We're going in a negative direction. We started at 0, and we're going down, so we're going in a negative direction. So notice whenever the acceleration is negative and the velocity is negative, both being vectors, they're working together. And it's like running with a tailwind. What's going to happen when you run with a tailwind? Is it going to propel you forward or hinder you? A tailwind is behind you, pushing at your back. That's going to make you run a little faster. Okay, that's what happens when you have acceleration and velocity, either both positive or both negative. Speed is going to increase. But if you're running into a headwind, it's going to slow you down a little bit. And that's when velocity and acceleration are opposite signs. The speed will be decreasing. So you can have velocity decreasing, but speed increasing. That's kind of important. Now let's do one last thing here. What was the acceleration? That's supposed to be another C. What was the acceleration at t equals 5 seconds when it hit the ground? That's instantaneous acceleration. Now I need to take the derivative of the velocity to get my instantaneous acceleration. And since I called it v up there, let me just write it again here. V of t is equal to negative 32t. So v prime of t, which you could call a of t, is equal to what? Negative 32. So a of 5 must also be negative 32 feet per second squared. Yeah. So for a falling object, of course, in ideal conditions, neglecting air resistance and all that stuff, the average acceleration should be the same as the instantaneous acceleration. All right. We're going to stop right there, actually, and tomorrow we're going to look at 13 and 14, and we're going to be done. 13 and 14 are going to show us how to force a piecewise function to be differentiable at a point, similar to what we did earlier when we forced it to be continuous at a point. And we're not going to use the alternate form. There's going to be a shortcut way to do it, and you're not going to want to miss it. But if you do, check out the video online under the shared tabs folder or click on the link that takes you to the YouTube video. All right. We did it. We did it. Lo hacimos. See? Should we do the dance? We did the warm-up and we got it right. Yeah, we did it. Did it. Yeah.